So I realized from the presentation that I was supposed to talk a little bit about the commissioning of this wonderful machine that is the Webb telescope. I do not have much today in my current slides to present you the commissioning, but I can simply summarize my role in there. So I'm a researcher at the University of Montreal, and I was part of the team that built one of the instruments on board James Webb, the NIRISS camera, the Canadian instrument. And I had the opportunity to go to Baltimore at the control center at the Space Telescope Science Institute, where the Webb telescope is controlled, where all the commands, the observations are received, sent. And I was there twice during the 6-month commissioning run, and it was fantastic to just see the first images coming on screen live. That was really amazing. So a great experience. So, but tonight I'm planning to actually talk a little bit more about the results, the first results that are coming from the first year of operation of the telescope. This is an exciting time, very exciting time to be working in astronomy. And we have the chance at the University of Montreal of having many students who work on the data that was just gathered from the Webb telescope. So let's give just a background story about exoplanets, which is my topic tonight, the first exoplanet discoveries. And I start with just a background of how planets form. So here we have a sketch of, on the left, a big dark cloud of gas that's been accreted from the interstellar medium in the galaxy that quickly condenses into a dark core after only a few tens of thousands of years. And very quickly, the star at the center forms, it starts shining, and the leftovers are found in the protoplanetary disk that surround that star after about 10 to the 5 years, 0.1 million years, very quickly. And after 10 million years, well, essentially all the planets are formed. The disk, the protoplanetary disk, is almost gone, and the star has started its life. So everything happens very quickly in the protoplanetary disk that surrounds the star. All right, so what happens for planet formation in that disk is the topic here. So the first step, as I said, is that the star forms and there's a leftover protoplanetary disk, and there's about a lot of gas in it and dust as well. But there's maybe 100 times more gas than dust in that disk. The next step is that dust grains coagulate. They collide, they stick together, very small grains, and they grow like this to become about pebble size, so the size of a few centimeters size. And pebbles are at the core of planet formation. Okay, so they are very important. And what happens as soon as you have pebbles forming in the protoplanetary disk is that pebbles decouple from the gas in some sense. The gas, you know, everything is revolving around the star, but the gas has this pressure that works with gravity such that the gas actually orbits the sun slightly slower than the dust. The dust itself follows like planet, is just gravity based. And so there's a mismatch in speed, which means that from the perspective of the dust, it sees a headwind. It sees the gas is breaking the pebble. And the net result is that it loses energy, and dust, the pebbles, start drifting inwards in the system. So you can imagine a protoplanetary disk, lots of gas, lots of pebbles, and all the pebbles are just drifting inward continuously. All right. And so for various reasons, overdensities of pebbles and gas happen along this disk. And as soon as there are overdensities, then there's what's so-called a streaming instability that kicks in. And a streaming instability will produce planetesimals, that is, like large bodies of about up to 100 kilometers in size. And I have here a depiction of what streaming instability here is. And I will actually show you even the movie. I hope you can still see that. Okay. And so you can, here we're in the disk, we're rotating along, okay? And on the left, you're toward the star, and on the right, you're going away from the star. And so there's a relative speed between those distances. And you see that you have streams of gas and mostly pebbles that go at different speeds, and they form streams. And it's along those streams that pebbles will accumulate or condensate to each other and form planetesimals. All right, so if I go back to my presentation. So once you have planetesimals, pebbles keep accreting on those planetesimals, and they grow in size, and planetesimals also form larger bodies. They also accrete to each other, and they form cores. Okay, they form protoplanets, and those protoplanets core are larger outside of the snowline and smaller inside the snowline. I will describe what the snowline is in a few minutes, but you can think of it as the region in space where water goes solid or vapor. That's the snowline. And so once you have large planet cores, well, they will start accreting exponentially the gas that surrounds them, and they will quickly become giant planets. For the small planet cores, they will not accrete gas, or very little, and their build-up timescale will be about 10 times longer than the giant planets. So for Jupiter, for instance, you can think that it formed in 1 million years, and Earth maybe 10 million years or even more. So that's a quick primer of how planets form. And I'm giving you this primer because it's important in the reasons why we are studying exoplanets with Webb. Another thing that I want to mention is the chemistry in the protoplanetary disk. You have gas, ices, and dust. Okay, the gas that I'm thinking about is the cosmological gas, hydrogen, helium. The dust is all sorts of irons and coupled with oxygen. So iron oxide, silicates, calcites, all those things. Those are dust. They are in solid form. Plus, you have the ices. So the methane, ammonia, carbonic, carbon oxide, water, all those things. Those are ices, and they tend to be in solid form far away from the star, and they become volatiles. They become gas when you cross their snow line. Each molecule has its melting point, and so you can imagine there are different snow lines in the protoplanetary disk. And as the dust forms, it accretes some ices, and this, as I said, the pebbles, the dust, they will migrate inward and eventually reach a point where volatiles, the ices, will evaporate, will become vapor. And so you can expect some sort of heterogeneity in terms of the chemistry. Inward of the snow line, you'll have more rocks, and outward more ices. So that's the snow line here depicted, and you see the arrow pointing at the pebbles making their way inward in the disk. And so, yeah, so that's why chemistry is not homogeneous across the disk. And so you can imagine then that planets forming far away will have more ice, planets forming closer to the star will have more rocks. And so that's the picture of planet formation today. Another thing that was never expected until we found the first exoplanets is planet migration. Okay, it was completely unexpected, but now it's fully explained. And the planet migration is that planets that you see now did not necessarily form or where you see them. They likely form elsewhere, more farther away from the star, and migrated inside through interaction with the gaseous protoplanetary disk. So here, and it's a phenomenon, it's purely a gravitational phenomenon. If you have a young accreting planet and gas around in the disk, this will create gravitational waves, waves of overdensity in the gas, and those overdensities will pull by gravity on the planet, pull and push, and the net effect is actually pulling inward the planet. And so the planets that form outside of the snow line, for example, will migrate inwards because of this effect. And that's the blue arrow going inwards. All right, so that gives you a background, and it kind of explains why we're interested in measuring the content of exoplanet atmospheres. The hope is that we may be seeing those effects of chemistries, and maybe we are able to pinpoint where the planets form just by looking at their chemistry, by the atmosphere chemistry. So that's one of the big goals of exoplanet study. And fortunately, we have tools at our disposal to observe exoplanets, and those are quick sketches that I will show just for fun. Okay, first we have this time series observation of exoplanet concept, where we stare at a star around which a planet orbits, and we have three ways of gathering data. So here we are assuming that our planet is seen edge on, so only a small fraction of stars in the galaxy have their planet oriented our way, right? Maybe 1% or even less. So for those 1%, we can either observe a phase curve when the planet orbits the star, and its reflection changes as a function of the phase, like the moon around the Earth. We can watch the transit. That's when the planet passes in front of the star and eclipses part of the star's disk. And when that happens, the starlight goes through the atmosphere of the planet, and it actually probe the terminator of the planet. It only probed that small region of the terminator. And not only is the terminator, but very high up in the atmosphere of the terminator. So we're measuring something, but that's the abundance of molecules very high in the atmosphere of the terminator of the planet. If we wait a little bit and the planet passes is eclipsed by the star, the planet disappears behind the star, then we observe an eclipse. And this eclipse gives us the information about the full integrated light coming from the day side of the planet. So it's a very interesting information. We can actually probe much deeper into the atmosphere, to the surface, if there's a surface. But the measurement is much more difficult to obtain because the signal is much smaller. So those are the three things: phase curves, eclipses, and transits. The transits are depicted here by this apparatus, a lamp, the light bulb that represents a star, and a fake planet surrounding it. And we are measuring the flux in red, and you see that there's a transit at every period. The transit depth, so how much the light intensity decreases, gives us access to the size of the planet that transits in front of the star. And assuming that we know the diameter of the star very well, then we can infer the size of the planet. On the left, you have a larger planet and makes a larger dip in the intensity. And on the right, you have a smaller planet making a smaller dip. All right, so that goes for the big rock planets. But how do we know if it has an atmosphere? Well, you have to look at a spectrum and look for absorption bands. So how does it work? So if we depict here the planet being transiting in front of the star, and we see that we have a naked rock planet here, all right, and it has a transit depth on the right. And if we put an atmosphere on it, the gray atmosphere here, at some wavelength in the blue, there's going to be a molecule that absorbs light. And so the planet will just appear bigger. The transit depth on the right will be just bigger. And so we'll be able to tell that at that wavelength that there's something absorbing that must be in the atmosphere. If you look in the red region where the specific molecule in the atmosphere does not absorb light, well, that's going to be another hint that it's this specific molecule that doesn't absorb light in the red, but only in the blue. And if you look in the green, then you see, oh, you have two absorption lines, so it must necessarily be this or that molecule that we're dealing with. So, so the signature of absorption in the spectrum is how we can tell if there's something and what is the nature of those molecules. And as you know, each chemical element has its spectral signature that uniquely identifies it if you take a spectrum. So those are just pure sketches and examples, but it gives you quickly an idea that we can infer the presence of vapor, water vapor, oxygen, methane, all gases that are in gaseous form. All right, so where do we start if we want to study exoplanets? We start with the low-hanging fruits. Those are the big planets that produce big transits, deep transits, and so they are the hot Jupiters. The hot Jupiters have a very puffy atmosphere, so it makes for even bigger signature in the spectrum. Something that we know about hot Jupiters is that they revolve very close to their star on a few day period. They have large temperature, 1,000 to 1,500 Kelvin. We know from Hubble and other telescopes that they contain water vapor. We already know that. We also know that they have clouds that sometimes block the light across the spectrum. So there's a mix of water vapor, clouds, and yeah. So here was the best knowledge that we had before Webb. This picture here, it's the spectrum of about 10 hot Jupiters acquired with Hubble, and so it lists the transit depth as a function of the wavelength of light, so the spectrum, and you can kind of guess or see that there is water here, but the strength of the water is not always high, it's not always big. Sometimes it's muted by the presence of clouds. At the bottom of this figure, you see mostly flat spectra. That's because clouds are higher up than the water vapor, and so it blocks and all the absorption by water vapor. And here is the first spectrum that we got using Webb. So that was published or officialized in July of 2022. It was the first hot Jupiter spectrum, and it clearly shows, so all the observations are the white dots, and the blue is a model for water, and it clearly shows the presence of water. It's not unexpected, but it's nice to see. And something interesting is that it covers a large wavelength domain. That's one of the big strengths of Webb. It has a large wavelength domain compared with Hubble. So, and this image or this spectrum was obtained using NIRISS. It's our Canadian instrument. That's a Canadian instrument. That's the instrument I worked on for 10 years before launch. All right. What else can we do with transit spectroscopy? We can determine size of planets. And if we do it for many planets, like this experiment, if we classify the size and the number of each planet, we can come up with distribution. So you have the small planets on the left and the big planets on the right. And you have their number, quantity, how many of them. And this gives us information. So this is the distribution density of exoplanets known as we launched Webb. And you will notice, so the size is in units of Earth size. So the Earth, you see, would be on the very left of this diagram, and we don't have the sensitivity or the yet to actually discover a lot of them. So we don't go to those small sizes. If you want, we only see the big planets, and you see something obvious. You see two peaks in the distribution. So you see that you have large planets and smaller planets and a gap in between. And so this gap is called the Fulton gap. And the peak on the left are the super Earths, and the peak on the right are the mini Neptunes. And you see then that the Jupiter-sized objects are actually they are under numerous. There's a smaller amount of those planets. They are quite rare compared with mini Neptunes and super Earths. And there's this gap in between the two populations that's quite intriguing. Could it be that on the left you have rocky planets without atmosphere, and on the right, like Neptune with big atmospheres? And if so, why is there a gap? Why are there not planets in between? It's one of the questions that we have with exoplanets. So a working hypothesis is that there's photoevaporation. Remember, those planets are usually found very nearby their star. It's a detection bias. We're more sensitive to planets close to their stars. And so because they're close, the radiation pressure from the star can probably blow away the atmosphere of the least massive planets, while the more massive planets could retain their atmosphere. So I depict this here. If you have two planets that start, they have the same size. One has a very small rocky core with a large gas envelope. One has a very big rocky core with also a large envelope of gas. If you let the star blow on these planets, the more massive planet will lose some atmosphere, but the least massive may lose all of its atmosphere. And so the working hypothesis to explain this gap is photoevaporation. Now, is this really happening? Okay, it's just the working hypothesis. And Webb, one of the first very exciting observations that it made of the exoplanet was during the early months after commissioning on WASP 39b. So a whole effort of the exoplanet community together, they observed with many different instruments of Webb, they observed the same planet and analyzed the spectrum. And here's the result. So we're dealing with a hot Jupiter again. And so the first thing, if you start from the left of the spectrum, you see water absorption features. So that was known, but those are really nice, good signal to noise ratio observations. What's really cool is as you go to the right, you see a peak at the right, that carbon dioxide peak. This is the first time that we saw carbon dioxide in an exoplanet. Okay, and it's a 1 year fresh. So it's the first ever detection of CO2 in an exoplanet. It's not unexpected. It's actually expected that we have some CO2, but it's the first detection. Something else that was totally unexpected is the sulfur dioxide, SO2 detection just left of that peak. This small sulfur dioxide peak, as I said, was not expected, but quickly they found why it's there. And they think it's because of sulfur molecules interacting with water vapor, and actually radiation from the star dissociating the water into O2 ions, and sulfur sticks to O2 and produces the SO2. So the presence of this molecule indicates that indeed there is a strong interaction of the atmosphere with its star through the radiation of the star. So it fits in the picture of photoevaporation, that there's a big interplay between the atmosphere and the radiation field. So that's a first very exciting result from Webb, and there's a few more I will show. Okay. So we turn our eyes to another hot Saturn this time. It's a 800 Kelvin. It's called WASP-18b. And what's funny about this one is that we observe the transit at the top right, and you see the transit shape, the intensity of light decreases, and then at the bottom there's a small bump, and then it comes back up as the planet passes the star disk. And this is not the first time we see this, but it can be caused by the presence of a dark spot at the surface of the star, and just on the same chord as the planet that passes in front. So the planet has passed in front of a star spot, and that produces that bump. So it indicates that stars are, more complex than you'd like to. There's a lot more things happening on the disk that you would like. Ideally, you would like a uniform disk, but things are more complicated than you want. And what's interesting here is that that's the spectrum, the full spectrum of I made a typo. It's HAT-P18, not WASP-18. So this spectrum shows small water vapor features, but mostly clouds. You remember when I said that hot Jupiters have water vapor and clouds? Here, it's mostly clouds that block the water vapor absorption. So there's a little bit of water vapor on top of clouds, but not much. What there is, though, that's interesting is this. If you look at high resolution, it's this emission line, or absorption, I should say, not emission, an absorption due to helium. And that's very interesting for our photo evaporation picture. Helium is a very, it's not a dense gas, okay? It's a very light gas, as you know. And so it tends to easily leave the planet. And that's what we're seeing here. The fact that it's a peak, a positive peak, means that there's more absorption. So the size of the planet and the helium wavelength is larger. And so you have a helium leaving the planet, and that's a confirmation. And so it goes in the picture that the radiation field of the star blows on the atmosphere, and some of the atmosphere leaves the planet entirely, and leaves, in this case, a gaseous tail for it of helium in there. So everything is consistent so far with what we expect. And we already, with those observations, learn a little bit more about, how planets evolve and form. So let me now go on a different tangent. Phase curves. So this is a different observation. So I've been posting observations of transits, but phase curves is another way to observe exoplanets. And you look at the star for a longer period of time. You look for the full year of the planet, so the full orbital period of the planet, and you look for the phases, so reflection by the of the starlight that changes as the planet goes around. This gives you also access to seeing the dark side of the planet and the bright side when it's on the opposite side. A big assumption that we're making here is that the planet is tidally locked with its star. And it's a very reasonable assumption to make, that you can calculate the physics and gravity, and it's almost certain that it's the case. So we're assuming that the planet is tidally locked, just like the moon is tidally locked to the Earth, and we see always the same face. And we take benefit of watching at different angles to recover the information of what the surface of that planet must look like. So James Webb observed LTT 9779b, a super hot Neptune, very hot, up to 2000 Kelvin, that has a very short orbital period of less than 1 day. Okay, and that's work that's being done actually here in Montreal by a student named Louis-Philippe Coulombe. And here's the final result, not published yet, of the mapping of this planet. And so it's very interesting. I will go a little bit into the details here. Essentially, you have here on the left, you have the blue wavelength, the wavelength associated with optical light. Okay, so you can think of it as the light that's reflected by the planet. And on the right, you have the red wavelength and the infrared wavelength. And you can think of that as the actual emission of the planet. Okay, and so on the left, you have the reflection of the starlight. On the right, you have the emission, intrinsic emission of the very hot planet. And you can see here that on the left, there seems to be, the planet disk seems to be brighter on slightly left of its center. And on the right, the yellow picture, the emission is well centered at the center of the planet. And so that's intriguing. At the top, you see the albedo as a function of the longitude, and it's a very high albedo, 0.6. So that means that it reflects almost all of the light that hits it. So it's a very reflective surface. How can you produce a very reflective surface? The answer is with clouds. Okay, and so think of this planet day side as being very, very hot, and think of the gas on the planet as rotating. It does rotate. Okay, there is motion of the gas around. Well, the gas sees day and night all the time, and there's motion. So as the gas moves around the planet, it goes from very hot to very, very cold on the dark side. And in doing so, when it gets cold, anything that was in vapor that becomes cold will condensate. There will be condensation, actual, droplets of solids, and when the gas and droplets of solid come back on the left side, and they come in the morning, they are still there, but they will quickly evaporate again. But for a few hours, they will still be clouds. And this is why, and clouds are very reflective. So this is why on the left, it's more reflective. So if you go back to this picture on the blue map, you see that it's brighter on the left. It's because there's still clouds on the left, and it's very reflective. And once the clouds dissipate at noontime, well, then the planet becomes a bit less reflective. So that's the picture that we build from those phase curves. And it's obviously you only have longitudinal information, no information about the poles, north, south. We don't have this information. All right. So that's a recent result. Okay, so let's move now to another topic. The topic of carbon-bearing molecules. So carbon is ubiquitous in atmospheres of exoplanets and everywhere, and it is expected to be in different form, in different molecules, depending on temperature in the atmosphere of exoplanets. For very hot planets, we expect all of the carbon to be linked to oxygen in the monoxide, carbon monoxide. But as you cool down the atmosphere, you can either have methane forming instead, or CO2 forming instead. And so on this diagram on the right, you see, how this CO becomes CH4 at a given metallicity. And here the metallicity is, you can think of it as how much rock dominated is the planet, or how much gas dominated is the planet. High metallicity is for smaller planets that are mostly made of rock. Their atmosphere also is very full of metals, metals being non-hydrogen, non-helium molecules or atoms. So small planets don't have much hydrogen or helium, so they are metal rich, and giant planets are metal poor. So think of this diagram as on the left side, you have giant planets, and on the right side, small planets. So is our picture correct? Can we see the change of molecule as we study different temperatures of planets? Do we see methane on planets that are below 1,000 Kelvin? For a long time, we couldn't see methane in those exoplanets, we didn't know why. So here's a first actually detection by Webb of methane. It was done with the NIRCam instrument, and by the second author. The first author is Taylor Bell. He's a physicist, astronomer, studied at McGill, did his PhD there, and he joined an American group for his postdoc, and he's made several discoveries. This is it's actually the very first methane detection on a planet that's less than 1,000 Kelvin. So on the top left, you have the transit light curve that shows clearly a very deep transit event. And at the bottom, you have an eclipse light curve. So they observe both the transit of the planet in front of the star and the eclipse behind the star. And those two give complementary information. On the right is the retrieved spectrum that they got from those observations, and as well as models for the different molecules. And they did the experiment of what would the spectrum look like if we removed water, or if we removed methane from the atmosphere. And so in blue, is the spectrum that you'd expect if you remove the water. So obviously, the real spectrum is different, which means that there is water in the atmosphere. And the purple is what the spectrum would look like if you removed methane from the atmosphere. And again, it's different, meaning that there's indeed methane in the atmosphere of that exoplanet. It's not the most spectacular spectrum, but it gives the result. And I will show you another example of methane a bit later. All right. And now come the time to turn our attention to rocky terrestrial planets. Rocky terrestrial planets are formed inside the snow line. They are smaller, rocky planets. There's not a lot of gas or ices available when they form, so it's expected that they form without atmosphere or very little atmosphere. In fact, we believe there's no atmosphere, and it's only later that their atmosphere is gathered by comets impact and this kind of stuff. We still think that's the case for the Earth, for instance. So, but in general, the question remains: do rocky planets have an atmosphere? And to give you the answer is we still don't know. We still don't know if rocky planets have an atmosphere. It's not because we're not looking. We have started looking with James Webb. We still haven't clearly detected an atmosphere around a rocky planet. But our hopes are very big, and the planetary system were giving us the most signal, or for which we're the most sensitive to atmospheres, is the TRAPPIST-1 system. The TRAPPIST-1 star is a very small red star of the spectral type M8. It's very small. It's at 10% of the size of the sun. And because it's very small, a planet passing in front of it will give you a big signal. And so that's what you need to make a good detection, is big signals, right? And so that's our best target to observe atmospheres around planets. So this system is famous. It's really famous, and so there's a lot of scheduled observation of TRAPPIST with Webb, and it's not on a single planet. This system has 7 planets. Amazing, one of the exoplanets with the most planets. So 7 planets, all of small size, so therefore likely rocky planets, not big gaseous planet. And on top of that, they're positioned near the habitable zone of the star. So the habitable zone, as you may know, is the region where the temperature of the planet would be just good enough to potentially have liquid water, or to be exact, it's the temperature where water would be liquid if there was water on the planet. Doesn't mean there is water, just if there is, it would be liquid. And so you have the planet D, the planet E, maybe C, that are in the habitable zone. So think of life and oceans, and so that's our hopes. Is there anything happening on those planets? It's the most hospitable planet that we know of, except Earth. But the first question is there any atmosphere here? Okay. And so, yeah, so that's what I'm saying here. Is there any atmosphere? And so the first cycle of observation, the first year of James Webb, is filled with scheduled TRAPPIST-1 observations. You see here a list of maybe a dozen different programs by astronomers across the world that study TRAPPIST-1, and they each target a specific planet around TRAPPIST-1, and with different methods, using the eclipse, the transit, no phase curve here, different instruments, MIRI, NIRISS, NIRSPEC, and for a different amount of times and different number of visits of observations of transits for each planet. So there's a lot going on. We are lucky here in Montreal to have a large amount of time dedicated on TRAPPIST-1. I'm not sure if Olivia Lim has presented a conference to you in the past, because she's the expert. She's a PhD student here. She's the expert on this and is publishing work on TRAPPIST. Anyway, the first Webb observation that was published is with the instrument MIRI. We observed an eclipse of TRAPPIST, actually 5 eclipses, and from the depth of those eclipses, it was found that actually TRAPPIST-1b is probably a naked rock, so no atmosphere on that planet. So how do we know that? Well, if the planet had some sort of atmosphere, the atmosphere would likely be heated a little bit by that heat from the star, and that heat would be redistributed on the dark side of the planet, and so it would not reflect much light. Okay, but here our eclipse depth measurement shows that it reflects as much light as it gets from its star, meaning that we probably have a surface, a hard surface that doesn't do any heat redistribution across the planet. So, yeah, so our hopes were not terribly high for this planet because it's the closest of all the planets, the closest to its star. So it's quite hot, 550 K, so a good 200 Celsius. It's hell, actually. And so, but it's here we have a proof that that's the case. So Olivia Lim also observed this planet with a different method, with the NIRISS instrument, and doing a transit. So trying to detect the top atmosphere of the planet. And here she presents the spectrum, the spectra that she observed. So if you look at A and B, those are 2 transits. They are the spectra of the planet TRAPPIST-1b at 2 different visits, and you see both visits differ. They are not exactly the same, and the signal is consistent with being flat, as if there was no atmosphere. So at the bottom 2 figures here, you have models of atmospheres. If that TRAPPIST-1b planet had an atmosphere with few metals or a lot of metals, you'd get the orange and green shape, and if at the very bottom, if you had the water vapor or CO2 in green, you'd get different shapes. So the data points don't show evidence of any atmosphere, unfortunately. But this is only the first planet out of 7, so there's still hope for the other 6. All right. Oh, yeah, I'm forgetting something. If you look at the top 2 spectra here, those are the actual extracted spectra, and they differ. They don't agree with each other. They should agree, but they don't. And it's not because we didn't do our analysis correctly. This was redone many times by different people, different methods. We all come with the same results. And the explanation is the transit light source effect, the TLS effect. And it has to do with the presence of spots and faculae at the surface of TRAPPIST-1 star. Those features that the planet does not cross over when it passes in front. Remember at the beginning of my talk, I presented you something when the planet passes on top of a spot, you see a small bump in the transit. In this case, the planet does not even cross a spot, but just the presence of spots causes a fake detection of whatever molecule there are in the spots. And in the spots, in a star spot, those spots are cold enough that water vapor can be found in those spots. So those water vapor in the spots introduce or induce fake water vapor signals in the planetary spectrum. So it's not a nice effect. It makes things a lot more complicated for our analysis, but it's there, and we clearly saw it overwhelmingly with our observation. And here I show you what our model is for a star. It's a uniform disk, and anything that's not uniform will introduce some kind of noise. All right, we're slowly getting to an interesting result. I will first talk about the water worlds. It's a kind of planet that is postulated to exist, and it would be a super Earth, so maybe 1.6 times the size of the Earth, and have a huge water vapor and water liquid ocean on it. And so this is a kind of planet that's supposed to exist, and we are trying to find this kind of planet in our data. And in Montreal, we have a student, Charles Cadieux, who has made not Webb observations yet, but has made other radial velocity measurements of the two planets around LHS 1140. One is 1140b, is the green spot here. And so here we have a diagram that presents the radius of the planet in the y-axis and the mass in the x-axis. So at the bottom left of this diagram, you'd find the small rocky planets like Earth. And on the right top side of this diagram, you'd find super Earths or mini Neptunes, so much bigger planets. And so the radius and mass together give you the density of a planet. And so the colored lines that you see here are different densities. Imagine a planet made of pure water at the top, the dark blue curve. It would follow this curve in the diagram, okay? Imagine now a planet made only of iron, 100% iron. It would be the bottom dash curve. If you had an Earth-like planet, it follows the plain black line. And so you see that there are two planets here of LHS 1140b and C are very close to that Earth-like track, but actually they are a bit bigger than the Earth's density would predict. Why are they bigger? Well, maybe they have some water content. So the water world is like a rocky planet with a big ocean, and that makes for a more puffy planet. And so that fits perfectly the picture here. LHS 1140b is perfectly in the domain of a water world. And what's really great about this planet is that Charles Cadieux was able to really get the error, the uncertainty very, very small in this diagram. So we have a very good idea of that it really is a water world. And the next step is to observe it with Webb to confirm this, if we can. And as for LHS 1140c, the purple on the left, well, it's a smaller rocky planet that seems to be pure rock. And so it's also a very interesting target to follow up with Webb because it is not suffering from that transit light source effect as much, because the central star is a more quiet star. We think it doesn't have as many spots and faculae, so we'll be better able to measure its spectrum without the noise introduced by the TLS effect. Which brings me to K2-18b, recently observed by the Webb Space Telescope. it's the archetype of the Iscian world. Iscian world stands for, so it's the super Earth, it's bigger than the Earth, and it's in the habitable zone of its star. Iscian stands for hydrogen plus ocean. So you can depict this as, so it's not exactly a water world. Yeah, sure, there's a water ocean, but its atmosphere is mostly, we think, made of hydrogen and helium, not of water vapor and more heavy gases. It's a water ocean with very light gas. So hence the term Iscian world. So in this case, it's a very nice temperature regime here. We're in 250 to 300 K, so clearly a habitable zone planet. If there's water, indeed, it should be liquid. And it weighs about 8 Earths. And here is the spectrum that they get from Webb. So it's a spectacular spectrum. You see on the left, if you see on the left at wavelengths of 1 to 1.5 micron, you see black dots, okay? Those are the data points of the Hubble Space Telescope. The only data points that we had of this planet with Hubble Space Telescope. HST observed it for 8 transits, and that's what it got. The rest is Webb. It's the large panchromatic, it's the large wavelength coverage of Webb. So it's an amazing improvement over HST. And so based on the previous HST spectrum, we thought that this planet had water in its atmosphere, water vapor. Okay, so we thought, oh, cool, it must be a water world or an Iscian world because it seems to have water vapor. But now, based on this spectrum, we realized that we made a mistake. It's not water vapor, okay? It's actually methane that's there. And so I encircled in black this region in the spectrum that shows here we have all of the molecules' opacity. So models of what each molecule introduces in the spectrum. Each component of the spectrum, each molecule has its opacity and creates some opacity and creates features in the spectrum. And so it's the strength of each molecule. So you clearly see that in green, CH4, so methane, is much stronger in this region than water. But we simply didn't have the whole picture, so we couldn't make a difference between water in blue and methane in green. So we thought it was water, but it's actually methane. That changes the picture because it's among the first 2 planets with methane detection in its atmosphere. So that's exciting in itself. But not only that, there's also CO2 on the right in the red bump. So if I come back to the actual spectrum, you have a red bump at between 4 and 4.5 micron. That's due to CO2. So you have methane and CO2 at the same time in the atmosphere. And if you had been to conferences before the launch of Webb, talking about exoplanet, biology and biosignatures in the atmosphere of exoplanets, astronomers would tell you if we have a sign of oxygen or methane or CO2 in the atmosphere, it points towards maybe life being there. If you have the presence of 2 of those gases, it clearly improves the odds that there's life. Okay, so here we have the case that we have 2 gases that are biosignatures. So it's quite exciting. And I think the authors of this discovery were very excited because they also included the molecule called DMS, the dimethyl sulfate molecule, and in their modeling. And so, and it's here in purple. Okay, the purple opacity is DMS. DMS on Earth exists at small quantities and it's produced by phytoplankton, by life in the ocean. And so clearly the authors were very excited and say, oh, maybe let's see if there's DMS in the atmosphere. And they got some detection of DMS that's really in a regime where is it noise or is it actual detection? So we don't know. We just know that there may be some DMS and potentially life. So think of phytoplanktons. Think of this planet as harboring a large ocean. It makes sense. You know, the temperature is about 250 to 300. If there was life there, the whole picture makes sense. But we need more observations to confirm this DMS picture. And so we don't often see astronomers being so excited in their papers or at conferences. But I was a witness of the excitement of this particular astronomer, who is an actually very serious astronomer. And here's the excerpt of his paper. He says that, you know, our potential evidence for DMS in K218b motivates consideration of possible biological activity on the planet. And he continues saying that on Earth, DMS is a byproduct of living organisms, with the bulk of the non-anthropogenic DMS in the terrestrial atmosphere being emitted from phytoplankton in marine environments. So it's exciting. And so I talking with my colleagues here, nobody really believes that there's actually a DMS detection, but it's worth, you know, making more observations to see if it is or not the case. So I'm essentially closing my conference with this. Of course, Webb is still a baby. It's only 1 year old, and there's much more to come. Among the things exciting is we will, for sure, almost for sure, find planets around white dwarfs. White dwarfs, remember, 98% of all the stars in the universe will end their life as white dwarfs. And since we know now that most stars do have planets, what happens to those planets when the star dies and becomes a white dwarf? Well, are they pulverized, or do they keep orbiting the white dwarf? And so it's almost certain that there are planets which just haven't found any, or just a handful so far around white dwarfs. Suspect Webb will find a lot of them. Also, okay, so this is actually a project that I'm working on, the planets around white dwarf. We do have a candidate, and I can show you if you want later. Another project I am personally involved in is the study of very, very small brown dwarfs. So brown dwarfs are, you know, in between giant planets and stars. They're in the gap in between. They don't fuse hydrogen, they don't produce light, but they are quite big. And so we did find a companion to one of the least massive brown dwarfs known, and it's probably something that's similar to a giant planet in mass, but it formed most probably like a star. So it's a planetary mass object, but probably formed like a star. So it's a weird beast. Where are we going with Webb? Well, we'll be doing panchromatic observations. That is, you know, observations with all the instruments taking as wide a wavelength range as possible. I've shown you that our HST picture could not tell, was so narrow that we couldn't tell between water and methane. With a large wavelength coverage, you can tell a lot more. And we'll perform the latest tools that we have, atmospheric retrievals. It's an analysis tool to find what's in an atmosphere, what kind of molecules. Webb has opened 500 hours of time to the exoplanet community to agree together to observe this year the most interesting planets that we can come up with. And so it's a plan that's currently being developed. Also, what we'll do is on the terrestrial planets, we'll probably sit for tens of transits until we reduce that noise level and we reach the ability of finding very small secondary atmospheres around those terrestrial planets. And maybe, who knows, we can detect molecular oxygen in terrestrial planets. And as I think it's clear now, is that the general trend is going for cooler, smaller planets. I guess because we're so interested by the complexity of those atmospheres, if we can detect them. And so that concludes my talk. I hope you have learned a few things. I hope you didn't fall asleep because of me talking endlessly. I will be open to questions. Of course, I enjoy questions. I have a few more slides about white dwarfs and the brown dwarfs if you're interested. Thank you.
Great. Thank you very much. What a wonderful lecture. I can't believe how much I learned, and hopefully it'll sink in. And but we will move to question and answers. So what we will do, we have we can take questions here in the audience at the library. Just raise your hand and Steve will come up to you with a microphone. And also we will take questions and answers from online for our Zoom participants. Just enter your question into the Q&A function and we will get to that. So yeah, let's lead off with an in-person question and we'll go backwards and forwards.
My question is related to flux. Why do you measure flux in ppm? Particles per million or particles per thousand?
Okay, so the question is, why do we measure flux in parts per million? I guess it's just a convention. It's we actually measure flux in units of photons, okay? But what we're interested in is changes of flux, okay? And since the changes are so small, then we talk in ppms, in parts per millions. Because if the signal was much stronger, we will be talking in parts per thousand. If it were even bigger, we would be talking in percentage. But since our signal is so small, we talk in parts per million. But it's just a convention.
Perfect. Thank you very much. I'm going to go to an online question now, and this goes back to protoplanetary disk formation. Does electromagnetism play a big role during the earliest stages of protoplanetary disk formation, or is it mostly just gravity?
Okay, yeah. Magnetism, magnetic field does play an important role in the protoplanetary disk, in the evolution of the disk. I'm not an expert on the topic, but it is modeled in the latest simulations. It will affect the inner disk will rotate as a rigid body to some extent because of magnetic field. But yeah, it's a good question. I just don't know much about it, but it's important.
Great. Any other questions here live in person? Just raise your hand. I'll go to another question online. Can some parallels be drawn to Saturn's rings where they will ultimately disappear and become larger objects?
Yeah, the protoplanetary disk is it's a phase before Saturn rings. The Saturn ring, we think, was formed when there was a collision between two icy bodies, and so you had particles, mostly particles there, ice particles. Not much gas, though, probably just ice particles. And in the protoplanetary disk, there's a lot of gas, actually, like and that you didn't find in Saturn ring. But yeah, the physics of what's going on for aggregating this into small satellites around Saturn is similar to some extent. Yeah.
That's great. Next question. If you could use any equipment to better observe exoplanets, what would it be? It doesn't have to be made already.
Well, that's a difficult question. It's an open question. obviously, I mean, one thing that we'd like is to have a high resolving power spectrograph in space with a very large aperture to be able to measure the wobble of planets, of very faint stars, around very faint stars and distant stars. Yeah, I mean, you could that way you could study terrestrial planets that don't necessarily transit in front of stars. So it would be amenable to the study of 100 times more stars to find the nearest planets around the sun. Ultimately, what would be great is a super large interferometer that could resolve the surface of stars, and who knows, maybe giant planets, but that's so far-fetched. I don't know how to answer this.
No problem. We got a question from here in the crowd.
Have we discovered any planet orbiting the first generation of stars?
So have we discovered planets orbiting the first generation of stars? So the first generation of star itself is not clear that we have observed. We are still, so the first generation of stars is something that the cosmologists are looking for. It's when the stars are formed when the cosmos has only hydrogen, helium, lithium, and stars are born out of this gas. So there's no carbon, no oxygen, nothing else. So you would, the first generation of stars would be stars, actually very large stars, but there would be no dusty leftovers, no material from which to form a planet. So the expectation is that there is no such thing as a planet orbiting a first generation star.
Okay, thank you. Another question here online. When you say that a rocky planet has no atmosphere, how can you rule out a very thin atmosphere?
Yeah, that's a very fair question. And we actually don't, so maybe I cut corners, but we don't actually rule out very tenuous atmosphere. Usually we talk about, confidence level of detection or non-detection. So this means that we have detected nothing down to some level of noise, and that doesn't mean that you couldn't have a more tenuous atmosphere that's smaller than the noise that you've reached. That said, if you have atmospheres that are denser, like one atmosphere pressure, usually we would be sensitive eventually with Webb. But something that's very tenuous, like 100 of the pressure of Earth, then yeah, it's so tenuous that you wouldn't detect it.
We got another question here in live here at the library.
Simon. Question about Dr. Sarah Sager. I see some of the research that you're doing at McGill and in the University of Montreal. What is Dr. Sager and her team focused on with James Webb? I know she's one of the pioneers in exoplanet research, and she's the honorary president of our society. So we kind of have a warm place in our hearts for her. Just curious if you have any insight there.
I mean, I think I've met her once. She is a superstar of the field. She really explored or developed the first ideas in the field of, for many topics in exoplanets. So she is probably a couple of steps ahead of many people, but she's a theoretician, right? A theorist. She mostly is thinking. And some of her students will actually take observations, and one of her students, Bjorn Beneke is now a professor at University of Montreal, and he carries a lot of observations with Webb. So she has this legacy through her students. But in terms of, I think she's so what is she thinking about nowadays? She's probably thinking about the next generation of telescopes and the capability that those will offer. And I'm not aware of any program on Webb that she leads actually, but I'm sure she's involved in a few of the programs as consultant, as you know, in the review process of papers. That's pretty much all I know, but she's a superstar in the field.
Thank you. A follow-on to that, I noticed the Sager equation. It's taking that data that you're capturing from exoplanet atmospheres, and it's an equation that Dr. Sager has submitted. That it's like the Drake equation, but it's not looking for intelligent life. It's looking for biosignatures and the probability of organic life based on biosignatures. I was quite interested in that last Hycean planet that you talked about. That looks like it could be one of the first candidates that may support or denounce that particular that particular theory of the Sager equation.
Yeah. I remember. I don't know I mean, I know what you're referring to, and yeah, she has been looking for potential biosignatures. So of course you can think of oxygen. That's the easiest to think about, but she has been trying to look for different gases, different signatures. And that's something that she really did well. I mean, she thought about many different gases, many different molecules, and tried to be thorough about what you could expect. I'm not sure if the DMS, the dimethyl sulfate that we're talking about here, I'm not sure if she thought about that first, or who thought about that first, but yeah.
Great. We'll move to another question here online, and it states, it seems that you'd like to find systems with stars that are close to ideal with few spots. Is that being done?
Is that being done? Yeah. So that's actually a big discovery that TRAPPIST has so many spots. We knew that it's active, so we can tell if a star will have spot or not. You know, you look at the variability. Photometry study, ground-based observation, oftentimes by amateur astronomers. You see if the star varies in time. And many M stars do vary in time. And you can there's a cycle, you can tell it's related to the rotation period. And so you can screen against those. If you want to do a web program, you will try to screen against those. But TRAPPIST was so interesting because it has 7 planets, rocky, that we had to look at it. We had to observe it. Now that we know that it's more tricky to analyze, people are slowly turning towards stars that are quieter, that don't show any variability, but still have a rocky or a small planet around it. Like the LHS 1140 example I was giving you, the BNC, that star is a lot more quiet and has a very interesting planets. So yes, it's actually in the process of sending projects to James Webb. The peer-reviewed of those proposals will put some weight on, is the star variable and active or not? And I suspect it may reject proposals where the stars are active.
Okay, thank you. Just have a few more questions here. Is it common for exoplanets to have water?
Yes, water vapor is the most ubiquitous molecule that we see in planetary atmospheres. And it doesn't mean that there's life there. It's just water vapor, or water is just a very simple molecule, one of the simplest molecules. It's everywhere in the universe. So it's not a surprise. Liquid water, we don't have direct evidence for liquid water. It's going to be hard to get any of those evidence. We'll always have only indirect evidence. We'll have indirect evidence by analyzing the content of an atmosphere, making a model for that planet, and inferring that there must be some liquid water down. We won't have a direct access unless, for some lucky reason, we have a naked water world without an atmosphere, and it reflects light. When you do a phase curve, it reflects light with those specular reflections. Maybe we could pick that up, but it's going to be hard to actually see liquid water.
Great, thank you. We got a question back here in the library.
Hello. Could you speak to James Webb Telescope's history? It seems like it was the telescope that was always coming, but I remember working towards it like 40 years ago, so it's been a while. You've been involved in it for a long time. How did it evolve?
Yeah, that's a nice question, because yes, the history of the Webb telescope is a long one, and my former supervisor, my colleague René Doyon, has a 60-minute conference about it. So it can be a long story. It started when, as soon as the Hubble Space Telescope was launched, the politicians and the NASA directors asked, so what's next? What are you going to do next? And astronomers gathered and said, oh, we're going to build a bigger telescope. Let's build a 4-meter telescope. And the response from the NASA head and the politicians was, wait, 4-meter, that's not ambitious enough. Build an 8-meter telescope. And so in the twist of events, the next generation space telescope, as it was called then, was an 8-meter telescope. And plans were made, and the limiting factor was the rocket aboard which it would fly. You had to fit it in the rocket. So it was reduced to a 6.5-meter telescope size. Infrared, because that's where we could see exoplanets, the early universe, star formation, and then the history is just, yeah, it was supposed to launch in 2007, I believe, in the beginning, got delayed several times. I joined the project in 2010. It was a very exciting time for us at that moment, because we had instruments problem. So Canada's involvement in Webb started with the fine guidance sensor. The Canadian Space Agency was contacted to be part of the project, and they said, okay, we can do the guider of the telescope. Essentially, the fine guidance sensor is the guider. And René Doyon here was joined the American instrument NIRCam, and he wanted to have a tunable filter imager in NIRCam, and was developing it until the Americans said, no, we don't want any involvement from a Canadian on our instrument, so no tunable filter in our instrument. René Doyon turned to the Canadian guider and said, hey, can we put my tunable filter on top of your guider or on the back of it? And we said yes. They said yes. And so that's why the guider became also a scientific instrument, NIRISS. And I arrived about then when we had some issues with the hardware, and we had to make a big choice of switching some instrument mode, remove that tunable filter, and put instead gratings and prisms and different filters to do an exoplanet mode. And so I had the opportunity to design the optics, contact manufacturers of the prism, test the prism in the lab, and then work on the pipelines to analyze the images produced by that exoplanet mode on board our Canadian instrument. And so, yeah, so there's a lot to say, but I think the hard work of René Doyon in particular here really made that we have an instrument, a Canadian instrument on board, James Webb. I mean, it took a long time because testing was so important. Remember, Hubble had a blurred vision when it was launched. And so NASA really didn't want this to happen again. And so they arranged to make an end-to-end optical test as one of the ground tests before launching. And that took a lot of money and time for it to happen. So they had to refurbish an old Apollo testing cryogenic tank, a 5-story high, and in order to make the Webb telescope fit in. And yeah, so a lot of testing is why it was so successful in the end and why it took so much time.
Awesome. Thank you very much for such a great answer there. We've got a couple small questions now that we can maybe just fly through, and then we'll maybe close this down at about 10 minutes. What is the limit for Webb for planet systems as far as distances are concerned?
I would think you want to observe the brightest planets because they give you the most signal to noise, the most precise observation. So you don't want to look for planets that are more than 1,000 light years probably. And in fact, you want to have well-characterized planets that have been observed on the ground with high resolution velocity, high resolution spectrograph. So most planets are going to be a few tens of parsecs away, so less than 100 light years.
Perfect. And just to follow up, how far from Earth are most of the planets that you described here?
It's in tens of parsecs. So think of 100 light years or so. So they're all very nearby. There are so many planets in the universe. We have to start somewhere, and let's start with the brightest ones.
No, I agree. That's great. Question here from the library.
How does gravitational lensing affect the stars you're trying to observe?
Okay, so gravitational lensing in this case here is not a concern. It's not we don't have to deal with this for exoplanet atmosphere studies. But lensing is a way of detecting planets, but it's a totally different way of detecting planets. And as you know, mass bends the space-time, and therefore the path of light is changed because of the passage of a planet or a star in front of another star in the background. You're looking at a background star, it's light, and all of a sudden the light intensity changes by a lot. It increases by a few factors, and that's a sign of gravity lensing. But you never know when this is going to happen. So you have to observe thousands and thousands of stars simultaneously, and suddenly one of them will turn on, and you'll say, oh, there's a planet or another star passing in front. You don't see that planet or star, you just detect its gravitational presence. And you can tell by the shape of the light curve how massive that object is. And in some cases, it's planetary massive. But once it's passed, that's it. You can't tell anything more. You can't observe it again unless you wait for 100 years, and you cannot learn more than that. So you have to look for many of those events and do statistical studies to get some insight into what's the mass distribution of those planets or the number of planets like this.
Great, thank you. Just a quick question. Can fusion begin in brown dwarfs? And if so, how?
Yeah, so I alluded to brown dwarfs at the end of my talk. I will not have the time to present our discovery, but brown dwarfs, it's by definition, brown dwarfs never burn hydrogen. Brown dwarfs do burn deuterium. There's a little bit of deuterium naturally in the cosmos. So when brown dwarfs form, deuterium fuses at a smaller temperature point. So brown dwarfs are are big planets, if you want, and at the center, it reaches a few 100,000 Kelvin, or maybe a million or so, just enough to burn deuterium for a short period of time, because there's not a lot of deuterium. And for that short period of time, it acts a little bit like a star, you could say, for a few million years. But after that, once the deuterium is gone, there's no other fusion that occurs in brown dwarfs.
Great, thank you. We've got a gentleman here who's raising his hand and would really like to ask a question.
Hi, Dr. Loic. It's me, Steve Donaldson. Thank you for an excellent talk, by the way. My question is simply that with the M-type dwarf stars are typically very active in their youth as regards solar flares. How do you think that would affect potential retention of atmospheres in the TRAPPIST-1 system? Thanks.
Yeah, that's a very valid question, a question that we keep asking ourselves. So when the M star is young, it's very active. If you compare it to the sun, it's much more active. So you can imagine if planets are there and they have an atmosphere, this activity may, and it's a lot of X-ray activity and UV activity, so hard, high energy photons, those may photo evaporate any atmosphere of a planet nearby. And so, yeah, it's a big question. Are there any atmosphere around M stars because of that reason? And that's something, that's an answer that we're seeking. We don't know, and that's why you need to make a study of many of those planets. And after 5, you can tell. After 50 planets that are naked rocks, maybe we'll start thinking, oh well, there's no atmosphere, never. But we haven't reached that point yet.
Great, thank you. A question from online. The outer planets of the TRAPPIST-1 system have such low densities that volatile elements are expected. Can you comment on which molecules, even if present, might be in states that can't be detected, like dissolved in oceans, for example?
Okay, so that's a very good specific question. So if so if you look at the TRAPPIST system here, you see my slides, I think, right? So you have the planet density in Y and the distance, and so you see that the density of the G planet is much below Earth's density. So it's the bulk density. We don't know anything about it. We don't see it directly. We can only infer its overall bulk density, and you could have some rocks with ices at the surface, and have a low density like this. I mean, it could be like a Titan, not a Titan. It could be a Titan, yeah, or it could be a Triton, or it could be a Pluto, or it could be a Europa-like object. So have a big atmosphere like Titan, like one bar, or have no atmosphere, almost like Europa. So we just don't know. And as in terms of if there's anything, what kind of gas or what kind of molecule, it should be like the regular ices, the same as what we see in the solar system on other bodies, nitrogen ice, carbon dioxide ice, and all these things.
Perfect. And just 2 more questions left. The first one, what were the biggest challenges in the development of NIRISS?
So NIRISS, the near infrared imager and slitless spectrograph. The biggest challenge was the deadline. We had literally a year to deliver the instrument once we decided that we changed its design. So we had the hardware, but we needed to change some of the filter wheel components And so the optics in there had to be, manufactured. And we had a year to find manufacturer, test the parts, and deliver the instrument. So that was the biggest challenge. It was a very intense period in 2010, 11, actually 2011, and we delivered the instrument, I believe, in 2012. So we ran very quick. It worked. And then it sat at NASA for years. We did three campaigns of testing during those years, but the last one was in 2016, and after that, it just sat at NASA in the telescope with the other instruments for so many years, for 5 years. So that was the biggest challenge.
Okay, no, thank you very much. And then just to close it off, just a question. What is your career like, and what would you say to somebody who would like to get more involved?
I like this question. I feel totally privileged to be doing what I'm doing. I often have how do you call this? The imposter syndrome. So I've started astronomy for me started when I was about 15 years old, when the Voyager 2 flew over Neptune, and I stayed up my first night without sleep, just watching the images coming down from Voyager. And I was very inspired in the months preceding, like seeing the small dots becoming bigger and bigger. And that's when I had my first, I made my first telescope. And so I was always more observation inclined, instrumentation inclined than physics and theory inclined. So I can't say I was a very good physics student. I was average and was just lucky. And that's where I say, I think I was just lucky in life to meet, for instance, René Doyon, my thesis supervisor, who gave me a chance, and then to meet him again after I spent 5 years in Hawaii working in the Canada-France-Hawaii telescope. Coming back, I had no job. Essentially, I was ready to do something else in life. And he contacted me and said, "Hey, would you like to work on the James Webb Space Telescope project?" So I thought about it for about a split second and said yes. But I'd say it takes some nerves sometimes to do physics and astronomy, because it's not seen as a way of making money or easy money. There aren't that many opportunities in that field, although there's more and more. But so it's a big risk. It's seen as a big risk. I was lucky to pursue that for until now. But in fact, any physics student that graduates has a better job rate or opportunity than even medical doctors. If you go through physics, you're almost assured to get a job, not necessarily in physics, but somewhere in life after that. So it's not that big a risk. So I would say, if you want to do astronomy, I strongly encourage you. It's a lot of fun, and it's not that risky, I think.
Great. Thank you very, very much for that presentation, and for answering those many questions that that came out today.